There's an interesting anomaly in electrical engineering in which electrical engineers settle for less than the best. They've learned to be mediocre, and then they take mediocre to be the conventional wisdom, and anything better is an impossibility. Well, Paul Falstad created a simulator whose transformers are ideal in the sense that they defy the Lenz law. LENZ, Lenz law, specifies the inability for transformers to pass DC. They can only pass AC. And the other thing that goes in parallel with that is back EMF. In other words, transformers in the real world, or I should say in the conventional world, fail to be ideal. They fail to do their job completely well. And the other thing that's a problem is that capacitors, for the most part, do their job very well, but coils do not, transformers in particular. And this is all because we've overlooked one little detail, a simple one. It's not little, actually. It's quite large. The core material of a transformer, we limit it to the interior geometry of the coil, thinking that's where you put it and it doesn't belong anywhere else. Yet it's that lack of core material that is at the foundation of transformers failing to be ideal, failing to be able to pass DC, and failing to defeat the Lenz law. Is not a law, it's actually just a convention. It's a rule of thumb based on this convention that we only put magnetizable iron or whatever material inside the interior of a coil or a set of coils that are acting as a transformer, and rather than extending it outside going beyond the interior of the coil. And when you're outside the interior of the coil, you've got the infinity of space to expand on the mass of that magnetizable substance to any degree you want to. This is what the Germans did, the Nazis, during World War II, when they converted some of their electro U-boats over to Tesla's special generator. I won't get into the details of the special generator. I mean, maybe I shouldn't. But it's very illustrative of the basic mechanics of electrodynamic theory according to the way it should be taught, not the way it is taught. We focus on amps and volts and watts, and that's the result we want. That's not the cause. The cause are dielectric tubes of force and what we conventionally call eddy currents, what are really helical spirals of electromotive force, which involve the current and the volts and giving us the watts. But the dielectric potential, see, the only difference between a capacitor, and that's another thing we do wrong. I'm sorry I'm jumping subjects. There's so much wrong here that has to be corrected. Capacitors we call capacitors as if that's all they do. Wrong. Inductors are inductors because they only deal with inductance. Wrong. Inductors, namely coils, and capacitors both do both functions to one degree or another. Now let's just take a coil that is obeying the Lenz rule of thumb, in which back EMF occurs. It's doing that because it's creating capacitance. The helical coil of electromagnetic force passing through the coil literally does an about face, and some of it turns around and goes back the opposite way. That's exactly what a capacitor does. It stops the helical electromotive force at one plate and tells it, hey dude, you're not going to pass me because I've got a wall of insulation here, the dielectric material. That's exactly what a transformer does, or a coil I should say, to some degree. And that tells me that the transformer is not ideal. It's not living up to its full potential of what it's supposed to do. It's supposed to... A coil and a capacitor has nothing to do with amps and watts. Those are the results. It has nothing to do with the causation. The causation is geometry of waveform. A capacitor is supposed to be able to pass tubular dielectric vectors of force, of potential force, and disallow the passage through them of the helical electromotive force. Meanwhile, a transformer, if it's ideal, living up to its full potential, is supposed to stop the dielectrical force, tubular force, but allow to fully pass, the helical electromotive force. And yet it doesn't. The capacitor does a better job doing its job than the coil of wire does in doing its job. And so we get this imbalance between the two. And this was very poignantly pointed out in the 1880s when the transatlantic telegraph cable was being laid and the electromotive force never made it across the ocean, the Atlantic Ocean. It would, but it would be delayed, and then eventually it didn't even reach the opposite shore at all. Meanwhile, the potential, the dielectric tube of force, what we measure as volts, or what we say the electrostatic, that made it across, no problem. So Oliver Heaviside did the math, came up with what we now call the telegrapher's equations, and then deduced from those mathematical equations how to solve the problem. Take the copper insulated wire, that cable, that they were laying across the Atlantic Ocean, and before you lay it, wrap an iron wire or an iron ribbon around it, not insulated, and then seal that whole arrangement with an insulative layer on the exterior. He invented coax cable, but instead of grounding the coax shield, he simply ran it as a parallel wire, which encouraged the formation and the sustenance, the maintenance of the magnetic field traveling down that iron wire. Meanwhile, the core or copper was maintaining the electric field. And they both ended up at the opposite shore in phase, with the telegraph, switch being able to switch on and off, giving dots and dashes, Morse code, like it was supposed to, instead of being a garbled mess. Well, we still have the same problem today. We have transformers or coils in general that are not designed ideally because they don't allow the electromotive force to pass completely through them without stopping it to a certain degree and converting it into voltage potential, the dielectric force. And that creates a lot of capacitance inside transformers, which might be a good thing if that's what you want, but if you want a free energy device, it ain't what you want. You want to defeat Lenz's law because it's not a law, it's a rule of thumb, because you want an ideal transformer that is capable of passing DC as well as AC. It should be able to do both. And this is what Paul Falstad's simulator does. His transformers can pass DC very readily, as well as AC, no problem. And this is where I got my initial training on learning electrodynamic behavior, waveform behavior, was in studying the behavior of monkeying around with his simulator. And I always wondered, well, why is his transformers different than his coils, and why are his transformers different than everybody else's, all the other simulators? It's because he's got an infinite amount of magnetizable iron inside that core. It's so massive, there's no way it's going to have any problem passing the electromotive force through it. Now, in order to imagine what these two forces are, let me paint the picture of a surfer. The surfer always hopes for the tube to travel not on top of the wave, but inside the wave as it's curling over him or her, creating a tube. And the wave crests, and then it falls over at one end of the beach, and the cresting process moves down the beach, one way or the other, right or left. That's the helical line of force, the helical electromotive force, forming the tube. The inside of the tube, though, is the dielectric pressure that creates the swell that we know of as a wave in the first place. And before the wave crests and curls over, that tubular force is rolling along as an electromagnetic style wave. Namely, it rolls like an eddy current. Imagine, if you will, a pencil, and you roll the pencil along the table. That's what the dielectric tube of force is doing as it approaches the coastline. It's literally parallel with the coastline, the tube, and it rolls towards it. And when it crests over and creates the wave, that's the helical electromotive force that crests at one end and moves across or down the tube to form and then close that cresting process. And of course, if the surfer positions himself or herself just at the right moment in time at one end where it's cresting, they can travel all the way down the tube as it forms and closes behind them. And they just ride the tube. Now, a capacitor cannot pass a helical electromotive force. And what happens is the helical force screws itself into one plate and tightens it up. And then it releases it and untightens it. That's charge and discharge. And as it's charging up one plate, it's actually allowing the tubular potential of what we call voltage, or the electrostatic force, the dielectric force, to pass through the dielectric. And an ideal coil does the opposite. It should stop the dielectric force and allow the helical, because they're at right angles to each other. When we say the magnetic field and the electric field are at right angles to each other, we make the mistake of creating a ripple or sine wave for each, which is false. False geometry. The correct geometry is that the so-called sine wave, which is just a two-dimensional representation of a three-dimensional helix, that actually is the magnetic field traveling along the surface of the wire, especially at high frequencies. Meanwhile, especially at high frequencies, the dielectric force is tubular going through the core of the wire, but at right angles. Now, this is important because Tesla made use of this in his special generator. He had two horseshoe shaped coils, and they were called his M coils. M as in Mary. Massive, thin wire, something like 50 miles of winding on each one. And they created a kind of a broken toroid because the 4 feet, the 2 feet of each, were facing each other. And a little tube reciprocated in the middle between those two. It went across the gap in the middle of the toroid and just to the edge, the outer edge of that toroid, and it reciprocated with compressed air. Now, the formation of that tube is very interesting because it's made of pipe in the sections that are not in between the opposing feet of the two, the pair of feet of each of the two horseshoe iron cores. In between those counter-opposing feet, it's some other material, and we don't know what it is. And I'm guessing it's a dielectric material that he is reciprocating through the cross-section of the toroid that he's broken by creating two horseshoe shapes that face each other, the feet. Because when you have a electromagnetic, or I should say a magnetizable toroid, you've got eddy currents, and the eddy currents are tubes of force that are rolling like the swells rolling towards the coastline, but they're rolling through the toroid at right angles to it. So the helix is like a wheel traveling down the toroid on the interior, but that wheel defines the radius of a tube that's rolling through the toroid, so that one end of that tubular wheel is facing, let's say, to the outer edge of that toroid, while the other is facing to the inner. And that's a weird way to depict it, but that's literally the way it looks, conceptually speaking. That's why the electromotive force can travel around in a circle in the core of a transformer until you tell it to do otherwise. And, PMH experiments, perpetual motion holder experiments that Edward Leedskalnin popularized, he didn't invent it. Literally, you can put an electromotive force into a steel bar that's been bent around into a U-shape, a horseshoe shape, and then you and then you create a complete loop by putting a flat bar at the 2 feet, and they're smooth as silk. You've sanded it down nice and smooth. You put a coil of wire around that and give it a little jolt from a 9-volt battery, and it'll hold that bar to the 2 feet indefinitely for years. You can even put a heavy soup can on there and it won't fall off. You've got to shear it off to get it off because the electromotive force is so strong it literally will not allow you to take it off. Or is it the dielectric force that's holding it together like glue? I don't know. They both work in tandem with each other at the same time, so it's obviously a combination of those two forces, but they're two different geometries. And that's the important thing. So I think what Tesla was doing was he was shaking up, he was vibrating the dielectric force inside a special generator. And he was also accentuating that voltage potential because the winding was thin wire, many turns, 50 miles on each horseshoe. So it encouraged the dielectric force over the electromotive. And then he took this tiny little rod and reciprocated 1/16 of an inch at 80 cycles per second to shake up that dielectric force traveling around those pair of horseshoe magnetized steel cores. Now the thing he did though, he bolted the cores of those M coils to the floor of the engine room of an Electro U-boat. An Electro U-boat is a submersible submarine from the Nazi era of World War II that ran on, it had electric motors and a bank of DC batteries, and they would normally surface and use a diesel fired generator to recharge the batteries, and then they'd go back underwater. Well, the Electro U-boats that were converted over to make use of Tesla's special generator, they ran on compressed air. They had the diesel fired generator, but they also had Tesla's special generator alternately running the generator to recharge the batteries, and they could do it while they were submersed underwater because they carried tanks of compressed air, actually liquefied air. They would flash boil the liquid in a special chamber, at a reduced pressure. So it would flash boil, turn to steam, and drive the piston. And the piston functioned like the reed in a wind instrument such as a clarinet or an oboe, in which the vibration never changed, never varied. So if it was 80 cycles per second, it was always 80 cycles per second. And this is important because when you have a massive hull of an Electro U-boat magnetically coupled to the core of these two massive horseshoe coils, you cannot afford the electromotive force, eddy current, elsewhere within the vessel to be oscillating at a frequency different than elsewhere within that huge iron ferromagnetizable mass of iron. This is why what we do a shortcut nowadays. We laminate the core of a transformer. But what Tesla did, instead of laminating it, he just made sure his alternating cycle never varied. That way, he would never have any problems and of loss of energy, and he could make use of this massive iron to defeat the Lenz rule of thumb. It's not a law; it's a rule of thumb. So we literally are substandard in today's world, and it's a shame and a pity, because it makes all the difference in the world when you're working with an ideal transformer in the real world instead of only in the virtual world of a simulator. And this is what Tesla did. He managed to do what we think is impossible. And when you start getting a coil to function as it should, living up to its full potential, and now you can do things with capacitors. Now, let's take the homopolar generator. We take a disk and we rotate it, and we stick it onto a magnet. And when we start, even though they're both rotating at the same speed, and they're glued to each other, that disk starts to develop a potential difference between the axle at its hub and the radius at its circumference. That's what a homopolar generator does. Michael Faraday discovered it. Well, what if you imagine that a capacitor is the same thing? Potentially speaking, it has the capacity of becoming a homopolar generator, but in a different way. It has the dielectric material now in between two plates instead of instead of the alternative of what we normally think of a homopolar generator. And then it has two plates. Now, if we start to vibrate or rotate a capacitor, The same thing's going to happen. We're going to have a homopolar generator now in an electrostatic sense rather than an electromotive sense. And it's very interesting because now we can get a capacitor to live up to its full potential, and that is to begin to behave as a negative resistor. All capacitors have what's called equivalent series resistance. Coils have series resistance in them, not only the resistance of the length of their wire, but they have inductive resistance as well. Capacitors, we don't normally think of them as having resistance because we think of them as infinite resistance. It stops the current dead in its tracks, and the current can't go to the other side. The voltage appears in opposite polarity on the opposite plate, but the current cannot go through. Well, that's not entirely true. So what electrical scientists have discovered is something called equivalent series resistance. It's equivalent to having series resistance in a capacitor. Despite the fact it's not there, it is there. And they're rated. If you look on Wikipedia, the article on equivalent series resistance, they're actually rated depending on the material you use for the dielectric of a capacitor. Ceramic capacitors have the least amount of equivalent series resistance, and aluminum can have the greatest, and tantalum and other materials in between. So if we start to vibrate a capacitor or rotate it very swiftly, we start getting behavioral characteristics that now start to look like negative resistance, in which the equivalent series resistance becomes negative, it's no longer positive, and we actually get more energy coming out of the capacitor than what we put into it. And so now, using these two techniques, we get a coil to behave as an ideal coil that can pass DC as well as AC and live up to its full potential of defeating the Lenz rule of thumb, which is not a law. And using this other technique, we can turn a capacitor into a homopolar generator, and it starts to generate current more than what we try to force across it, which won't go across it, but more comes out the other side, which could never go through it in the first place. It starts looking very weird. And when we start to do these two things, just these two changes in our thinking, now we got free energy at our fingertips. We can do whatever we want. The world is our oyster at this point.